Hello, math students. Greetings from me, Miss Benoli. Alejandro has informed me that my videos need more fun greeting and jokes. So I have a joke for you. It's a math joke. Here it is. What happened to the plant in math class? The answer is, it grew square roots. So there you go. If you have a better joke, you can submit it to me and I can maybe include it in my next video. So here we go. Now that we're all happy and relaxed, 3.3 is graphs of nonlinear inequalities. So we treat nonlinear inequalities just like we do linear ones, and we've actually done a few examples of these in the recent weeks, so it shouldn't be anything too new. So again, you're just like we do with lines, you want to decide if it's dotted or solid, and you want to find the points where the solution lies, so where to shade. You can do that obviously by plugging in points. So this first example here, determine whether these 4 points are solutions to this inequality. So all you want to do is just test these points out. So the first one is going to be -4 for y, and 3 for x. The next one will be 7 for y, 4 for x. The next one will be 1 for both values, and then 6 for y, and -1 for x. When I do this math out, this is going to give me -4 less than or equal to -2. That is true. This one will give me 7 is less than or equal to 1. Not true. This one will give me 1 less than or equal to -2. Not true. And this one will give me 6 less than or equal to 6, which is true. So the points 3, 4, -4, and -1, 6 are 2 points that lie in the solution of this inequality. Notice this is a nonlinear function. It's a squared function, so it's a parabola. So we would graph a parabola and shade a region around it. Okay, so here's how we will graph. This first one here is a cubed function. Those are the graphs that look like so. We're going to use our knowledge of translations. So this graph is going to be down 2, and this graph is going to be to the right 4, and I'm going to have a solid line. So my original graph is going to be in black here. Looks like at 2 I'm at 8. 1, 2, 3, 4, 5, 6, 7, 8. Looks like this. That's my original graph. So I'm going to translate this point down 2 and to the right 3, 4, 1, 2, 3, 4. And I will look like so. Okay? And then I want to figure out where to shade. So just like with lines, I can test the point 0, 0 and see what I get. So 0 is greater than -4 cubed minus 2. -4 cubed is 64. Minus 2 is going to be -66. 0 is indeed greater than that, so you would shade towards the 0. Same idea on the right here. We have an absolute value function. I'm going to have a dotted line because it's not equal. I'm going to be shifted to the left 2, up 3, and I'm going to be reflected across the x-axis. So that looks like, let's see, up 3, 1, 2, 3, to the right 2, 1, 2, and shifted down over the x-axis. So it looks like that, except I forgot dotted lines. Oops. So this should be dotted, dotted. Okay, and again, testing a point. So I want a point that's clearly on one side or the other. 0 is clearly, 0, 0 is clearly on this side, so we can test that. 0 less than 3 minus absolute value of 0 minus 2. That's 0 greater than 3 minus 2, 0 greater than 1. Not true. So I'm going to shade away from 0, 0 and look like so. So again, nothing new. Just remember dotted or solid lines, testing points, and then graphing your parent function with the appropriate. So here's one for you to try. Y is greater than x minus 5 plus 4. So try that one out and put your answer on the provided graph. Okay, next example is we want to solve an absolute value inequality algebraically using the definition of absolute value to determine the solution set. So when I say use the definition of absolute value, what that means is understanding that the part of the function that says x minus 2 in absolute value form, that must be positive. But that value in and of itself, x minus 2, can be positive or negative. So there's two different values that can go into that absolute value sign, and then whatever value goes in there comes out positive. So there's two cases that we want to test for. We either have to say x minus 2 before its absolute value is taken is either negative, or x minus 2 before its absolute value taken is positive. So we need to test those two situations in this function. So we're going to say negative x minus 2 minus 5 is less than 4. And we're going to say positive x minus 2 minus 5 is less than 4. When we do that, we get negative x plus 2 minus 5 less than 4. That's going to be negative x less than 7. Divide by the negative 1, and I need to flip the sign. X is greater than negative 7. There's my negative. This is x minus 7 greater than 4. Move the 7 over. X is, less than 11. So I have two different solutions. X either has to be bigger than 7 and less than 11. So I can write that in a couple of ways. With set notation, this is saying x is the set of all numbers such that x is between negative 7 and 11. So x is a value not equal to negative 7 or 11, but somewhere in between. You can also test this by graphing. And how we do this is we take the original function here and we split it into two different functions. So notice there's no y in that equation. So what I can do is I can replace the left-hand side of the equation with a y and say y is less than 4. And then I can replace the right-hand equation of the with a y and say the absolute value of negative 2 minus 5 is less than y. So I've just replaced each side of the equation with a y, creating two separate inequalities, and then I can graph those. So y less than 4 is a dotted line at y equals 4, okay, and it's less than 4, so it's everything below this line. And then the absolute value of x minus 2 minus 5 is the absolute value down 5 units for 5 and to the right 2 units here. And again, I'm a dotted line. Okay, this is going to intersect at the point negative 7, 4, and 11, 4. When I test a value in here, if I test 0, 0, I'm going to get 2 minus 5 is less than 0, which is negative 3 is less than 0, which is true. So this one shades in. So the solution of those two inequalities is that area there. So that's just a way to check the solution, but to solve it algebraically, you need to test for the two situations where where inside the absolute value is negative and inside the absolute value is positive. So why don't you try this next one? It's the exact same idea. You can solve it algebraically first, and then you can graph it to check your solution. you should get that x is less than -1 or x is greater than 9. So that's your algebraic solution, and you should be able to check that graphically as well. Okay, that's it, and hopefully this is still review material. We will do some more practice in class and go from there. Have a good day.